Okay, so we had already started talking about the aldehydes and the ketones. So one concept that I want you to learn is the organometallic compound. So even from the word organometallic, this is a compound that contains a metal and an organic compound. Organic compound basically is a carbon. For example, you can have where I've got a metal with, you can see something like this, the metal. Metal can be anything, sodium, potassium. Okay. So when the carbon is attached to sodium or to potassium, those bonds are largely ionic. When carbon is attached to lead or tin or thallium or mercury, those bonds are going to be covalent in nature. And the carbon to lithium and carbon to magnesium bonds will be in those regions where you have is going to lie between being ionic and being covalent. So when you have got a metal, you can see magnesium. It attacks an alkyl halide, it displaces the alkyl group. You form the organometallic compound. And when that organometallic compound, actually what was happening here is that you don't displace the metal. Instead, the metal is grabbed by the magnesium. The R group remains alone, that we form the organometallic compound. So organometallic compound, when it gets now that same R group, you now form a compound like this, and that's known as the Grignard reagent. Okay, look at this one. These are practice questions. You want to predict the product of these reactions. You can see we are having water and we are having a Grignard reagent. So when you have got this compound, organometallic compound, where the magnesium, that's what we call the Grignard reagent. Grignard reagent. So when this guy is reacting with anything, it will act as the nucleophile, because normally, when you have got a carbon atom is normally positively charged. It acts as an electrophile. It is attacked. But how about if you want the carbon atom to attack? That's how you now attach the carbon to the organometallic compound. So this carbon attached to another group like this. Can you see it's attached to an R group? Okay, it's actually attached to a magnesium, which is attached to X, this Rx. The R itself is a carbon. Now when this bond breaks here, you know that the breaking of a bond, carbon and the metals always lose electrons. So it will go like this when this bond breaks. So what you are going to have is carbon with two lone pairs of electrons. So for a Grignard reagent, the carbon is always negatively charged, and so it acts as a nucleophile. That is what you need to understand. Okay? Please, that is very important. Like for these mechanisms that you've written here, we want to show the product. So first thing first, for the first one, you have got this. As long as you see MgBr, or it can be any metal, the first step that happens that this bond is broken. The carbon takes the two electrons. Then you are going to have this. Carbon is now negatively charged. And then another product you have is MgBr. This is going to be positively charged. Now this, you have formed your carbanion. It is going to act as a nucleophile. And you know the nucleophile is supposed to go under attack. So here you have got this. This is your water. So this thing is going to attack water, it's going to grab this hydrogen, this bond breaks, and so you end up forming this. You have an hydrogen that has attached. Normally, you don't even show the hydrogen. So that is going to be the product. So you can see that we actually form alkanes when we're using the Grignard reagent, alkanes. That is going to be the same with any one of these things that you're able to see here. It's going to be the same mechanism. Let me just pick one because it's basically the same for everything. That will be the same with this one. First, the bond here is going to break. So you have this. Here you are going to have a lone pair and a negative charge. So this one now will go and attack. You can see here you have got this compound like that. But remember, this is acting as a nucleophile. So as a nucleophile, we are always grabbing an hydrogen because the aim is we want to form an alkane. So you can see this alkane. And then this thing is not having an oxygen. To be the same for this one, just remove the lithium and then this carbon will remain negatively charged. It will now go and grab the hydrogen. So basically that for everything, that's the mechanism. Now the Grignard reagent can also react with epoxides. You know what epoxides are? They are ethers, and ether is where I've got oxygen bonded to arar groups on both sides. But where the arar groups ends up forming a complete ring, that forms what we call an epoxide. So this is an epoxide. So an ether, what is going to do, well, the Grignard reagent, what happens is that, again, it is in this form. First thing is this bond breaks such that the arar takes up the two electrons, it becomes negative. So this is going to now go and attack one of the carbons, which is attached directly to the oxygen, and that will break the bond there. You can see where this arar is going to attach, it's going to attach here. So it's going to be like oxygen, like so, like this, and then the arar is attached here. Normally you want to write this straight. So carbons are these 1, 2, 3. So I'm going to have it like the 1, okay, 1, 2, 3, and then you have got arar group here, and by also add oxygen there. So this is what happens, but this oxygen is going to be negatively charged because remember we have broken a bond, so that's why it's negatively charged. And this oxygen with a negative charge, you know, you have got a lot of compounds in solution. It can go and grab a hydrogen like from protonated water, like this, to come and grab this hydrogen. This bond ends up breaking. That's how you end up forming now an alcohol. It's the same with all these other compounds. Okay, but take note of this, that this came in your tutorial sheet 1. Take note that the Grignard reagent will react primarily at the least substituted ring. So in a case where you have got an epoxide like this one, you have got another group here. This Grignard will come and attack this carbon instead of attacking this carbon which is more substituted. Yes, the alcoholic is the reaction, but mostly you even see it, it will be part of your reactants. They'll write it somewhere. They are going to show, but if they, even if they don't show, normally you don't want to end up with a product that is charged. Okay. Now the same Grignard reagent can also react with carbonyl groups. Carbonyl group can either be a ketone or an aldehyde, like this. So if you have got H here, as long as at one end there is a H, that's an aldehyde. Even when both are H's, it's still an aldehyde. But if both were carbons attached to a double bond with oxygen, that's a ketone. So the Grignard reagent reaction with aldehydes or ketones, remember first thing first is that we are removing the MgX. We are remaining with R, which has a negative charge. This is the one which is going to attack the carbon containing the oxygen. Every time you do that, the bond here always breaks. Okay, so this is what happened here. And we ended up forming something like this. We had our R group and then oxygen. This oxygen is negatively charged. The next thing is that the oxygen will grab an hydrogen from a protonated water or hydronium to form now an alcohol. So that is the mechanism. You see, when you react a Grignard reagent with aldehydes or a ketone, you form an alcohol. Look at this. Is this an aldehyde or a ketone? Have you seen where the two hydrogens have circled? Is that an aldehyde or a ketone? Yes, it's an aldehyde as long as you have got an hydrogen at one end. So when you have got an aldehyde like this one, and also an aldehyde like this one, when you react an aldehyde in this form with a Grignard reagent, you are going to form a primary alcohol. But when you react this Grignard reagent with the this alcohol with the Grignard reagent, you're going to form a secondary alcohol. But in a case where you react a ketone with a Grignard reagent, you form a tertiary alcohol. So that's why you can see here the alcohol is secondary because the carbonyl group that we started with was in this form. It had one end with an hydrogen, the other end had a carbon, like here. Yes, yes, depending on the type of aldehyde that you have. But for a ketone, there is no way it can form primary or secondary alcohol because these two groups are both R groups. So when the Grignard attaches here, you can see we have got three R groups, and the three R groups, that is the tertiary. Esters can also react with Grignard reagents and they form tertiary alcohols. Look at this. The R comes and attaches here, its bond breaks. This is an ester because we have got OR. And then the oxygen will come back to form a double bond. And then we get to push back this group. You can see you form a ketone. Okay. This ketone, if you add more Grignard reagent, can further react with the Grignard reagent to form now our alcohol. You get the sense. So end up forming a tertiary alcohol. So these are some Grignard reagents that you can see. As long as you can see MgBr, Mg, just know that's Grignard reagent. So basically break this bond. So we are going to have something like this with a negative charge here. So in this case, this guy is going to come and attack here, breaking the bond. That's why you can see at this carbon, we have attached a carbon, which was supposed to have a double bond with oxygen, but now the oxygen is a single bond. Don't worry about this MgBr because oxygen is going to be negatively charged. So the MgBr here just comes close to neutralize that negative charge. Otherwise, this oxygen is negatively charged. Using the protonated water to grab one hydrogen from there, and that now forms the alcohol, benzyl alcohol. That's the same mechanism with this one. Reaction with a ketone, you can see the same thing that is happening. We've already described this. We've described also the reaction with an ether. All right. But take note of this. Look at the Grignard that we started with. First thing is this bond is going to break. We're going to have something like this. Two electrons with a negative. This will come and attack here. This bond breaks. We end up forming something like this. Of course, the MgBr will not be there. This is going to be negatively charged. And then when it is an ether, one lone pair will always leave the top and come back to form a ketone. Okay. And then now we use another Grignard. If we had more equivalents for Grignard, for example, if they said two equivalents, and this again we'll get to remove the MgBr, so remaining something like this, which is still negative, and this will come and attack here, breaking this bond. That still forms this one with a negative charge, and this now can grab an hydrogen from solution to form our alcohol. Okay, we can look at this one. How would you carry out the synthesis, the following synthesis? Look at what you have. You have got this guy, you end up with this guy. How do you think we can carry out this synthesis? Any idea? Yes, Olik? The Grignard? Mm-hmm. Okay, can you give me the structure of the Grignard that you're going to use? Mm-hmm. How many carbons should be there? So just look at this. This is one, two, three, four, five. Five carbons. Look at the product. How many carbons does it have? One, two, three, four, five, six. This tells you that the Grignard you should use should only have one carbon. So this is going to be the first reactant. Second reactant, like just protonated water. Because in the first step, what happened? Yes? Okay, you can see from the reaction from the reactant, look at the reactant. The reactant has got one, two, three, four. Actually, this one has got four carbons. My drawing here wasn't right. It was supposed to be like this. There are only four carbons. So if you see, we are starting something four carbons, but look at the end product. It has one, two, three, four carbon here. The fifth one is this one. Sixth one is this one. So this should tell us that we actually having more. How many carbons more? These were four, but these are five. tells us that we compound that we used had two carbons, two carbons. Okay, something like that. Does that make sense? Because if we get the 4 and the 6, if we add the 4 plus 2, it should give us the 6 carbons. Does that make sense? Yes. So that is what happens. But look at the actual mechanism now. You can see we have got the Grignard, but here we are only using two carbons, and you see why. This carbon, when it goes and remember, we always attack the carbon with a double bond. We attack the carbon with a double bond. What happens? So initially we said, remember, this is why for you to answer a question in chemistry, you first need to know the theory before you can know the mechanism. We said if you are talking about an ester, the reaction is going to move by two steps. The Grignard will attack in the first step and then to attack in the second step. So because we're moving from 4 carbons to 6 carbons, the first attack should be 1 carbon. Okay, this Grignard. So basically I'll just remove the Mg, so we'll just remain with 1 carbon, and that one will come and attack. That remove this, and we are going to have this. This is going to be negatively charged. Remember we said that as long as it's a keton, it was an ester, one bond comes back, and then the other bond attached to the oxygen will always break, and that forms the next product. So we form back our double bond. So this is how it was supposed to be. But now this one is no longer going to be attached to the other, and this guy is going to be negatively charged. This guy is supposed to grab an hydrogen because we are going to have water, protonated water. So this is 1, 2, 3, 4. Okay, you can see this carbon. 1, 2, 3, 4. And then this is now, remember this is 1, 2, 3, 4. 1, 2, 3, 4. And then we have got an OH at the end there. What happens in the next step is what? Another Grignard, the same as the one that we had used earlier, will come in. Just 1 carbon, isn't it? So this will again come and attack. This bond also gets to break. Okay. And when that happens, we'll go up. My drawings are apart here. Let me just explain using the same one. Okay. So, yes. Mhm. Now, here we're supposed to have a carbon. When the Grignard, I just forgot to write that. When the Grignard attaches, we include, because it, remember, the Grignard was the one which was attacking. So this guy is supposed to be included here. So even here, it is still going to be there like this. Don't forget it, otherwise you'll not write the correct mechanism. This one. Now the next thing is that when the second one attaches, it is attaching again, right? So let me try to write it on top here. So here now we're going to have a single bond, the negative charge. So from this one, we are attaching another group like this. Now this guy will again grab an hydrogen from a protonated water. That's why we end up with OH here. So that's basic the mechanism. It's what you can see here. Should be the same with this one here. There's nothing complex. You can see that it looks complex, and they'll bring this one because they know students will think it's complex. I think they brought it last year or something. So just identify the Grignard. This is the Grignard, and they've told you it's two equivalents, so you should tell what that means. So first, this bond is going to break. So now you have got this, and here you are going to have two electrons with a negative charge. This is going to go and attack. When it does attack, this bond will break. And so you have got alternating bonds there, and you have a single bond here, the negative charge. You have got Cl. Remember, you have attached this group. What happens next? Double bond comes back, removes the chlorine. So I've got a double bond with oxygen. You have got this guy this side. You also have the same guy this side. Don't forget they are benzene rings, so they have got alternating double bonds inside. Because we use two equivalents of this guy, it will come in again. The alternating bonds, it has got a lone pair there with a negative charge. This will again go and attack. That breaks the bond. So we end up attaching another ring. But then initially it is going to be oxygen because we have broken the bond, the negative charge. This is going to grab an hydrogen from ammonium chloride. And then we are going to end up with this guy which is here. That will be the mechanism. It's not any complex, right? Not complex. So what you are seeing is that when you have got the aldehyde, because the Grignard reagent is basically providing you can convert an aldehyde to an alcohol. Ketones also, but just depending what type of alcohol are you going to convert. Esters we've also seen, you can convert them. But one important thing that I want you to take note is that there are two other reactants that we can use, and these are known as reducing agents. We can use the sodium borohydride. We talked about these reactions, remember, when you're talking about alcohols, and lithium aluminum hydride, or La. This can be used to reduce our carbonyl groups and convert them into alcohols. We had also mentioned, if you just follow the video on alcohols, to say lithium aluminum hydride is much stronger reducing agent than sodium borohydride. That's why you can see when you have got an aldehyde where you have got one group here and one and an hydrogen. When you use sodium borohydride, you are going to form the same product as when you use lithium borohydride. But then when you use a ketone, even a ketone, you still end up with the same products when you use any one of these reducing agents. But see how it changes when you talk about ethers. Ethers will be reduced to form an alcohol using lithium aluminum hydride, but the reaction will not happen in sodium borohydride. That is the same with carboxylic acids. And this is very interesting because immediately they give you a carboxylic acid with sodium borohydride, they want you to write a mechanism. There is no reaction. That's your mechanism, no reaction. If you end up writing something, that's wrong. So lithium aluminum hydride is a much stronger oxidizing agent. You have other oxidizing agents. Now, sorry, these are reducing agents, all right? Reducing aldehyde ketones, esters, and carboxylic acid into alcohols. Now you have got also oxidizing agents. These ones will be able to oxidize. Okay, you have got the Swain oxidation, also PCC, pyridium chlorochromate. We talked about the mechanism already. Primary alcohols can be oxidized into the aldehydes. Please take note. PCC only oxidizes up to aldehydes. Okay. If we use the chromic acid or potassium dichromate, these are strong oxidizing agents. They don't end at this level of an aldehyde or a ketone. Swain oxidation or PCC is a weak oxidizing agent, so it will end at the level of a carbonyl group, either an aldehyde or a ketone, depending with the type of alcohol you started with. While chromic acid or potassium dichromate always form the acid, you can see you're ending with a carboxylic acid. Carboxylic acid. This one was an aldehyde. If it's a secondary alcohol, you form a ketone. This one is also forming a ketone. This one is also forming a ketone. Because for secondary alcohols, you cannot form an aldehyde by all means. There is no space of where there is a hydrogen where you can touch an oxygen to form an acid. Okay. Tertiary alcohols do not undergo any oxidation whatsoever by any agent, oxidizing agent. And this mechanism can be used as a test for alcohol or to identify groups. So if they asked you in the exam, how can you, this one came, I think they brought it in test 2, they also brought it in the exam. How can you differentiate a secondary alcohol? Give a simple test to differentiate secondary alcohol from a tertiary alcohol. You can simply get one of these reagents. You can say, using PCC, secondary alcohols will yield ketones, but tertiary alcohols don't show any reaction. You've answered. If it's 2 marks or 4 marks, you get it. You can also get to hydrate alkenes, a triple bond. When you react it with water, you form a double bond and can convert it actually to, you can convert it to a ketone. And the mechanism is, remember we are reacting with, this is known as acid catalyzed hydration of alkenes. You are reacting alkenes with water, but then you are using an acid as a catalyst. So first from the acid, sulfuric acid, which I can write it like this, we are grabbing an hydrogen from the sulfuric acid. This bond breaks. Every time you grab an hydrogen, it is going to attach to the carbon with more hydrogens. So it will attach here. And so when it attaches, the one bond breaks because the carbon here cannot have 5 bonds. That's why one bond leaves, and then the positive charge will attach where the hydrogen didn't attach. Now, positive means you are an electrophile. So water will now attack the electrophile attaching here. And then another water will come and remove an hydrogen. We end up forming this guy. Now what happens is that one lone pair from the oxygen will automatically come and break. And then that will break the double bond. Actually, the double bond is going to go and grab an hydrogen from a protonated water that was formed from this water which grabbed the first hydrogen. And then you are going to end up with this compound. We have formed a double bond with oxygen. By then there is a hydrogen on top, so this means that this oxygen is positively charged. So I can grab that hydrogen out. That's how we end up forming a ketone using this mechanism. Now there are various tests. These are tests to identify what type of carbonyl group you have. We have got the Brady's test. The Brady's test, you get to react, you should have done this experiment in your chemistry. You react 2,4 dihydrophenylhydrazine or 2,4 DNPH. So just know when you just see 2,4 dihydrophenylhydrazine, that is Brady's test. And what is this test about? It is basically there to test carbonyl groups. Okay, you want to distinguish aldehydes and ketones. So when this reaction is positive, you are going to see a yellow or orange PPT. You can see this precipitate, right? So that is what you are going to be able to see. And when it is positive, it means that you have got a carbonyl group. Please take note. Positive Brady's test means that there is a carbonyl group. It doesn't matter whether it's a ketone or an aldehyde, it's going to be positive. Any question? Okay. Yes. It's really not important. It's not important the mechanism here. Okay, I'll show you the questions that they can ask you, which they brought last year. So this is the mechanism by which the reaction happens, but I haven't seen it being asked. But for the sake of the sake, you can know the mechanism. You can see this compound has got it has got what's the group? A carbonyl group. And this is 2,4 dihydrophenylhydrazine. Basically a benzene ring, and then you have got two nitro groups, skipping a carbon on the middle, and then at the end you have got a nitrogen attached to one hydrogen and attached to one amine. You can see the product that you produce. To that one hydrogen which was there, you basically remove the hydrogen. To one nitrogen, you basically remove the hydrogen, and then you attach this girl group and you remove the oxygen. Okay, so that is what happens. Okay, the second test is known as the tolerance test. Now, the tolerance test, you basically, the most important thing is that it is just positive for what? Aldehydes. So immediately you hear tolerance test was positive, just know that you had an aldehyde. You didn't have a ketone aldehyde. And the test is that you are going to see a silver mirror. But how do you know that what you were reacting with was a tolerance test? What is the reagent? It is silver nitrate. So if they tell you that you reacted your compound with silver nitrate, you got a silver mirror as your product, that means that the reaction was positive and that you had an aldehyde. Please take note. It is negative when you're talking about a ketone. That is very, very important. Okay. Any question? Any question? Okay. So the next test is known as the Fellings test. Fellings test again, take note that it is only positive with the aldehydes. And the color that you'll be able to see is going to be a red precipitate. Okay, red precipitate. And one important thing, what is the reagent? The reagent is, you are going to see copper and sodium hydroxide. So we are done with the test. Now what is remaining is for us to do just some practice questions. Are we good? Yes, please. You can go on. Yes, as at now, just know that. But I'll see if it's necessary. But it's not necessary for the mechanisms. I've included also the mechanisms, but it's not that necessary. The last test is the iodoform test. But just look at the mechanism, just look at how they are going, all right? It's very vital. The iodoform test, it doesn't test whether you are talking about aldehydroketone. It just tests for any compound that has got a terminal methyl. You can see this methyl that is at the end, that's the meaning of terminal methyl. It will give a yellow precipitate. If you just see a yellow precipitate when you react with iodine and sodium hydroxide, just know that the iodoform test is positive, meaning that your compound, whatsoever the compound, it can be an aldehyde, a ketone, an acid, it has got a terminal methyl group. Yes, please. There is a question. Okay. So now let's look at some questions. These were from last year's tutorial sheet 4. And they actually brought the same questions. Was that test 2 or the final exam? It should be both or one of them. The same questions. Predict a major organic product with the following reactions. Mechanisms are not required. You can see for the first one, we are talking about a Grignard. Okay, so basically for the Grignard that we have, all you do is remove the MgBr, the bond comes here. So we're going to have a negative charge here. This guy is the one which will go and attack here, right? Breaking this bond. So we're going to form this. Remember, this guy is coming to attach. So let me put a methyl here. This methyl that is already there. And then this one that I'm taking to attach there, let me put it here. Remember, this one has got an oxygen and another group there. Remember, when you break the double bond here, what is at the end here will grab an hydrogen to form an OH. So this is going to be our product. Oh, by the way, remember that you add also this here. It's a very easy it's a very easy reaction. Yes, please. Okay. So the one that happens twice is when you have got an ether. Ether. Okay. Actually, an ester, not an ether, an ester. You have got this. You have got an oxygen somewhere, and then it continues like that. Continues like this. When you have got an oxygen here, it will happen twice. But you can see these guys are only ketones. So it only happens once. So that is going to be the same with this other guy here. So the Grignard is basically going to, so I'm going to put the methyl down here. The Grignard is going to attach from this point. Okay. Make sure that you count the carbons well. So that's carbon number 1, this is carbon number 2, this is carbon number 3 before the oxygen. So 1, 2, 3, and then oxygen. And then you have got a methyl at the end. This one, remember, when you break it first, you are going to have an oxygen with a negative charge, and then it will grab an hydrogen. So this will be the product. This question, test 2, they just got it the same way it is. Yeah, it was a lot of marks. It should be 14 marks. And these questions were like, should be two of them. One was 14 marks, one was 20 marks. So if you get those two wrong, even if you get the rest of the questions correct, you are gone. Give the structure for compounds A up to E in the synthetic scheme. So we are starting with cyclohexano. If you acidify it, look at what you are producing. Now you need to know what cyclohexano is. Cyclohexano is an alcohol. Cyclo means 6 carbons. So this alcohol like this. Now, what reagent is this? This is a dichromate, potassium dichromate. This is an oxidizing agent. And we talked about oxidizing agents in alcohols. We actually talked about each one of these. In case you have forgotten, the tutorial video is there on the drive. Okay, the reactions of alcohols. Just go on that video, reactions of alcohols. So when you oxidize an alcohol, what you end up forming depends with the type of alcohol that you have. Look at this. This carbon attached to the oxygen has got two other carbons. This is a secondary alcohol. Oxidation of secondary alcohols forms the ketones. So here, after this reaction, the first product, which is A, is going to be a ketone. And so this is going to be like this. This is A. And you can see, you can even tell from the structure, 6 carbons, only 1 oxygen, and then 10 hydrogens. So I've got 2 hydrogens here, 2 here, 2 here, 2 here, 2 here, 2, 4, 6, 8, 10. You don't have any hydrogen here. That balances with the formula. And then after that, you are reacting with the Grignard reagent. Remember, when you react, this is a Grignard reagent. When you react a ketone with a Grignard reagent, you are forming an alcohol. So you basically, this Grignard reagent only has got 1 carbon. So you are going to have it there, and then this is going to be OH. Okay, so you can see I've just introduced the 7th carbon. The 7th carbon, that's why I've got 7 carbons here. So this is the structure B. And then the next, look, we are reacting with an acid in the presence of heat. When you react an alcohol, we talked about this in the presence of heat. An alcohol in the presence of heat, that is known as acid catalyzed dehydration of alcohols. An alcohol plus an acid and then you heat, that is dehydration. So in a dehydration, what happens is that this oxygen will first grab this hydrogen and then the bond with the air will break, and then we are going to form protonated water, and this is going to be a good leaving group. Okay, it's going to leave, and then what happens is now your A minus is going to come and grab an hydrogen at one of it will actually grab an hydrogen, can grab an hydrogen here or an hydrogen here. When it grabs that hydrogen, the bond breaks, it comes here, you form a double bond. That's why we call it acid catalyzed dehydration. Dehydration ends up in the formation of alkenes. So what you are going to see as a product here is going to be this. You are going to still remain with the methyl, then you have got a double bond. You can see that's why oxygen has disappeared here. This is going to be the product C. And then the next thing, we are reacting with ozone. Now this is ozonolysis. Remember, when you react an alkene with ozone, you break the bond on the middle. You break the bond on the middle. So this is going to be a carbon here, a carbon here, a carbon, a carbon, a carbon, a carbon, and carbon number 7. So carbon 1, 2, 3, 4, 5, 6, 7. You can see at carbon number 6 and 7. Let me number this 1, 2, 3, 4, 5, 6, 7. At carbon number 6, at carbon number 6, this is where we have to break the bond. That means that there is actually a double bond. And in ozonolysis, you attach an oxygen there. And then at carbon number one, also that's where there was a double bond. That's why we had to break it. So there's actually also a double bond there. Just attach an oxygen. Had we used the not methyl sulfate, if we use the hydrogen peroxide, we would have formed a carboxylic acid, would have also attached OH at the carbon that is at the end with an oxygen, not this one here because this is a ketone, but on the aldehyde end, you always attach an OH. If it was what? If it was the hydrogen peroxide, but here just attach an hydrogen because it's a dimethyl sulfate. Balance with the formula, you have got 7 carbons and 2 oxygens. These are the 2 oxygens. If you count hydrogens, they're going to be 12. After this, we are getting now this guy reacting it with silver. Uh, just look at silver ammonium hydroxide. This guy, silver ammonium hydroxide, is what we call this one. Look at these tests. Look at this test. This one. That's known as the Tollens reagent. It's positive with what? Aldehydes. Okay. The other reagents, Brady's is dinitrophenylhydrazine. Toluenes is where you use nitrate. Okay. Phelines you use copper. Iodoform you use iodine and sodium hydroxide. So this guy is the Toluenes test. Now the toluenes, when you react an out is positive for what? You know that toluenes is positive for an aldehyde. So basically what you do is that when you react an aldehyde with toluenes, you convert an aldehyde into an acid. So this same compound here, 1, 2, 3, 4, 5. Is it like this? Here I've got double bond with oxygen. Okay, again like this, 1, 2, 3, 4, 5, 6, 7. Okay, we had the double bond with oxygen. So can you tell me between this one and this one, which one is the aldehyde between 1 and 2? 1 is the aldehyde and toluenes is positive for the aldehyde. So at the aldehyde, and that's where we're going to attach OH. And you can see I've introduced another oxygen there. So this is the structure E. So this was it for this one, writing all the missing structures. And then this one, a compound with formula C5H10O. Yes, please. Yeah, this one, the mechanism when we are talking about it wasn't required, but we just had to know that the dichromate, the chromic acid, these were oxidizing agents, and you know that these are strong oxidizing agents, isn't it? You know, oxidizing agents will convert secondary alcohols into ketones, primary alcohols into carboxylic acids. If it is a strong oxidizing agent, a weak oxidizing agent will convert the primary alcohol into a ketone, an aldehyde, for example, PCC. Is that okay? Okay, good. A compound with the formula C5H10O gave a positive reaction with Brady's reagent. So now let's start interpreting. Already from the saying, it gave a positive form. It gave positive with Brady's reagent. That tells us that it is an aldehyde. Gave a negative reaction with phelines. If it gave a negative reaction with phelines, what does that mean? Remember, the phelines test is a test for aldehyde also. If it is negative, it means there is no ketone. Okay? If it is positive, let me write this so that you understand as a quick, interesting summary. So we have got the tests for the aldehydes, the ketones, and also the color change they are going to give us. The first one is the Brady's test. Now, Brady's test, what do you use? Is 2,4 dinit dihydrophenylhydrazine. Actually, dinitrophenylhydrazine is positive for aldehydes, negative for ketones. If it's positive, you are going to get a yellow to orange precipitate. The next one is the Tollens test. Tollens test, what do we use? We use silver nitrate mixed with some sodium hydroxide. This one is going to also be positive for aldehydes, negative for ketones. It's going to give us a silver a silver mirror. The next test is the Fellings test. And for the Fellings test, what we use is basically copper with sodium hydroxide. And this guy is going to be positive also. By the way, Brady's test is a test of all carbonyl groups. It's positive for anything that has got a carbonyl. Unless the Tollens and the Fellings, these two are only positive for aldehydes. And this one gives us a red precipitate. The last test is the iodoform test, and it is a test of a methyl terminal methyl group, iodoform. How do you know that it's iodoform? You see a mixture of iodine with sodium or potassium iodide or something that has iodine. It's terminal methyl. Doesn't matter where it is, terminal methyl. And this one is going to be giving us a yellow pipette if it is positive. So now we can answer the question. A compound in the formula C5H10O gave a positive reaction with Brady's. Brady's, it means that it has got a carbonyl group, but we don't know what type of carbonyl group it has. Gave a negative reaction with Fellings. So with Fellings, if it is negative, it means that what? It gave a negative test with Fellings. What does that mean? It's not an aldehyde, isn't it? It's a ketone. Okay, just from the word negative Fellings, it's a ketone. And when treated with 10% iodine and potassium iodine in sodium hydroxide, it gave a yellow pipette. What does it mean? It's positive iodoform, meaning that it has got a terminal methyl. So it is a ketone with a terminal methyl with 5 carbons. So let's draw 1, 2, 3, 4, 5. Terminal methyl, just leave a methyl at one end. It's a ketone. This is a ketone with a terminal methyl. What possible structure can we draw again? I can write like this. Okay, like that. This is how many carbons? This is 4 carbons. I'll get the last methyl and put it here. Okay, that still works. So these are the two possible structures that I can draw. You can see they have got a methyl at the end and they are both ketones. Yes, please. Mhm. It's supposed to balance this formula, but make sure that there is a methyl at the end. So we're making sure there is a methyl at the end. At the same time, it's balancing the formula. That's why also for this one, I still left the methyl there, but I just changed the position of the last carbon. Is that okay? Okay, good. An isomer of the same above compound, they've said this is an isomer, gave a yellow pipette with Brady's. So meaning that it is positive with Brady's, uh, it still has a carbonyl group. And a red pipette with Fellings. Now this one has a red pipette with Fellings. The meaning of that is that it's actually an aldehyde because it's positive for Fellings. It's an aldehyde. And then they've said, and no reaction with 10% iodine or potassium, meaning that there is no terminal methyl group. Draw the structure of all the isomers that will react. So you want an aldehyde with that formula, and it shouldn't have any terminal methyl group. So carbon 1, 2, 3, 4, 5. Just put the double bond at the end. This is an aldehyde. You can see there's no terminal methyl group. Okay, this is an aldehyde. As long as the group is at the end, it's still an aldehyde. Or I can draw it like this. This is three carbons. The fourth one I can put here. One, two, three, four. The fifth one I can put here. Or I can draw like this. One, two, three. I can put the fourth one here, the fifth one here. So these are the possible structures that we can draw. They are all aldehydes. Yes, please. It should always be there. Then immediately I put any methyl at one end and then the double bond comes on the middle. It's no longer now there is a ketone. Okay. Okay, there was also this question, but this is like acids. This should be the next topic we are going to do. Acids F and G have pKa values 4.2 and negative 3.3. This is very simple from just your chemistry for last year. When you have got a high pKa, it means you are a weak acid. So meaning that this one which has got a low pKa, G is a strong acid. Which is more acidic? G. Give a reason for answer, the pKa. Okay, upon reaction with the base, which of these two acids would form a salt with a pH greater than 7? Now, pH greater than 7, you want to use a weak acid. Because when you react a weak acid with a base, okay, the 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 product is going to have a pH near the strongest thing you used. So weak acid, let's say we are using a strong base. So the reaction is going to have a salt which is basic. If you use a strong acid, it's very hard for you to neutralize the entire strong acid. So you end up with an acidic salt. So for part 2, the answer is F. That is the same with this one. All these questions, they actually brought them in test 2. All these. Between phosphine and ammonium, which would you expect to be stronger than? Now, these guys, they are not from this topic. So we'll do them when we cover the acids in the next topic. They are very easy questions. But questions like this, we actually even answered them because topic 1, this is the topic that I started explaining how you can determine a stronger nucleophile. And you know that the stronger the nucleophile, the stronger the base because they are the same. We talked about that. That would be also the same with this one. How do you know which compound is going to lose an hydrogen? We talked about just topic 1. If you go in topic 1, nucleophiles and electrophiles, you'll be able to answer the entire of this question on the drive. Just follow topic 1. It will be way easier such that even when we do the next topic, it will not give you any problem. Okay, or this one. Which of these below do you expect to be stronger? This is the first topic that we started with. If you remember, we actually answered these questions in that class. Maybe this one. Maybe we can answer now this one. Okay, let's go. So what is this one saying? We are being told an unknown compound A readily decolonizes a solution of bromine. Anything that decolonizes a solution of bromine is having a double bond. Okay, just know it has a double bond. And then we are also told that when A is dissolved in cod, when A is dissolved in cod concentrated sulfuric acid, and when heated with water, B is formed. So I want you to follow the steps as they are being outlined very well, because if you miss any one, it will be very hard for you to be able to answer this question. An unknown compound A decolonizes solution of bromine, meaning that it has a double bond. When A is dissolved in cold concentrated sulfuric acid and when heated with water, B is formed. You can see the formula for B. And B will react with chromic acid to give C. Both B and C give a positive iodoform test. What does that mean? What does that statement mean? Methyl group at the end, all right? And each iodoform reaction mixture contains, in addition to CHI3, an ion of butyric acid. What is the unknown structures of A, B, and C? Let's start with the last statement. Okay, we can start from the beginning. Unknown compound A. You can see this compound only has got 5 carbons. Doesn't have any oxygen. So it is 1, 2, 3, 4, 5. Because it decolonizes bromine, what is supposed to have a double bond, but we don't know where the double bond is going to be. Double bond can be at the beginning. Double bond can be on the middle. If I put it here, it will still be like this same one. And if I put it at the end here, it will be still like the first one. So these are the two possible structures of A. But one thing that we've been told is that when A is dissolved in concentrated sulfuric acid, you know what happens when you react when you put something in concentrated sulfuric acid and heat with water, you form an alcohol. So if it is this one, what alcohol are we going to form? We are going to obey the Markov-Nikov's rule. Okay, so the hydrogen is going to attach to the more substituted compound. So the OH will come and attach here. I'm not writing the mechanism because we already know that. So for this one, this is what will form. For this one, which is down, there are two possible products because none of these carbons is more substituted than the other. So the chances that we can form the same product as the one on top, or the OH can actually come and attach here. So these are the possible structures of A, these are the possible structures of B. And then we've been told that this will react with chromic acid to give C. You can see, you know that a reaction with chromic acid, that is what? Oxidation. Convert an alcohol into a ketone or an aldehyde. So this is going to be the product for this one. For this one which is down, the product is going to be this one. But we've been told that both B and C give a positive iodoform test, meaning that they have got a terminal methyl group. This one, this B doesn't have a terminal methyl. This B doesn't have a terminal methyl. This one has a terminal methyl. This one has the terminal methyl. So you see, so the structure for A is this one. Structure for B is that one. Structure for C is this one. So that is the answer for this one. Yes. So if you look at where the OH is attached, look at the groups attached. This is an ethyl. Even this one is an ethyl. So there's no methyl there. So that's why it is disqualified. That is the same at this point. They are ethyls and not methyls. Good. Okay. And then there's also this one. Compound A, C5H12O, does not give a pipette with phenylhydrazine. Does not give a pipette with phenylhydrazine. What does that mean? Hmm? We've already forgotten. Okay. The meaning of that one is, you remember phenylhydrazine is a test is Brady's reagent, so meaning that it doesn't have a carbonyl group. Brady's reagent is for carbonyl groups. So compound A is not a carbonyl, and oxidation of A with potassium dichromate gives B. Compound B readily reacts with phenylhydrazine, now meaning that B is now what? B is now a carbonyl group. And then they've said, but does not give a tolerance test. What does that mean? It's not a ketone, it's an aldehyde. The original compound A can be dehydrated with sulfuric acid to give hydrocarbon. Okay, so meaning that we can get A, we convert into an hydrocarbon with 5 carbons. 1, 2, 3, 4, 5. This is a structure C. And ozonolysis of the hydrocarbon C will yield acetone. So if we break this compound, I've not put the double bond first. I don't know where I need to put the double bond. But when we break this compound, we're going to give acetone and acetaldehyde. Acetone is like this. Acetaldehyde is just like acetone, except that at one end you have got an hydrogen. So you can see these are 5 carbons. And when you form a compound like this, what compound did you break it from? So you can write like this. This is the best way in which you are able to know from where you had removed something. So now just remove the oxygens, merge this compound. So it was like this. You can see 1 carbon, 2, 3, 4, and 5. This is 5 carbons. So this is how the structure was. So there's actually a methyl here. Okay. And then there's a double bond on the middle. So let me write this where. So this compound was supposed to be like this. Like that. This is C. But remember, this C is coming from what? A. The original compound A can be dehydrated. We removed the water to be able to form this compound. Now remember, dehydration of alcohols form alkenes. So what would be the possible structure? Basically, go in the backward direction. When you get an alkene, you hydrate it, you form an alcohol. And hydration of alkenes will form alcohols. The alcohol is attached at a more substituted carbon, right? So this carbon here is more substituted. So the alcohol was actually like this, like that. Apart from this, another possibility that we would have had was the alcohol being like this, where the OH had to attach here. Remember, when you're hydrating, you'd rather form a more substituted guy. Okay, so these are the two possible structures of A. But we know that A does not give a precipitate with phenylhydrazine, so it's not a carbonyl group. Oxidation of A with potassium dichromate will give B. So oxidation, this is where now you should tell which structure between the first one and the second. Oxidation with dichromate will give B. Remember, we said that tertiary alcohols don't undergo oxidation. So just that statement disqualifies this one. Because it's a tertiary alcohol, it can't undergo oxidation. So this is going to be A. And A now can be oxidized. And then you'll be able to form a structure like this. And this is a ketone. And that follow obeys because they've said that B does not give tolerance test, meaning that it's a ketone. Only ketones are negative with tolerance test. So we have written C, we have written A, we've written also B. Okay, so that is it. That's how you interpret that. How would you distinguish between 2-pentanone and 3-pentanone? This also came in test 2. Okay, 2-pentanone. These are what? So pentanone 5 carbons, 1, 2, 3, 4, 5. 2-pentanone is like that. and then 1, 2, 3, 4, 5. See the 3 pentanone is like this. These two guys are both ketones. The only difference is where the OH, the double bond with oxygen, is attached. So 2 pentanone, can you tell that it has got a terminal methyl group? So can you tell me how can you differentiate these two guys? So you can use the iodoform test. It's going to be positive for 2 pentanone and negative for 3 pentanone. How do you distinguish between propanone and ethanol? Ethanol, what ends in -al is an aldehyde. In one, it's a ketone. So prop, 1, 2, 3, double bond here. And then ethanol, 1, 2, double bond here. For the sake, let's just put an hydrogen here. Okay. This is what we also call acetone and acetaldehyde. How do you think we can differentiate these two guys? Aldehydes react with Tolen's test. Oh, this is not the aldehyde, it's this one. They react with the Tolen's test, and they also react with what other test? Okay, they also react with the Felling's test, and with the Felling's they'll give a red PPT. With the Tolen's they'll give us a silver mirror. The ketone doesn't do that. So that was it for this tutorial sheet, and this is the topic. Next time we start the organic acids. We are remaining with two topics to be done with the entire course.